I welcome everyone in the today's session, which is on multiple access techniques for future radio access for 6G wireless communication. In this session, we'll take a look at different various multiple access methods. We'll begin with the basic multiple access techniques which have been used traditionally in the wireless systems or communication systems. Later, we'll move towards the advanced multiple access methods or techniques which we are going to use, or some of the recent technologies they are using them. We will begin with frequency division multiple access. Then we'll cover the basics of time division multiple access, code division multiple access. These three were the traditional multiple access methods which have been used across the generations of various wireless communications. We will cover them to refresh our basics, and then we'll move to the advanced multiple access techniques such as space division multiple access, which is also known as SDMA, orthogonal frequency division multiple access OFDMA, non-orthogonal multiple access NOMA, and the hybrid version of OFDMA and NOMA also. And at the end, we will also take a look at the rate splitting multiple access. We'll cover the basics and then we'll move towards the advanced one. There are a few more advanced versions such as, let's say, spectrum filtered OFDM, which is also known as FOFDM, which is the advanced version of OFDM, overcoming the various shortcomings. We will also take a look at filter bank multi-carrier non-orthogonal multiple access, which we have already decided to go through. We'll also take a look, if time permits, pattern division multiple access, generalized frequency division multiplexing such as GFDM, SCMA, sparse code multiple access, and there are various more. If time permits, we'll go through each of them. What is the use of these multiple access methods or techniques in wireless communication? As we know that the resource or frequencies are limited and they have to be accessed across multiple users. Therefore, we have to allocate our frequencies or other resources in such so that as many users can access them at the same time. And that's why we need multiple access methods. We have to share a finite amount of radio spectrum, because we know that the radio spectrum is fixed and limited, and it is very expensive also. Each telecom vendor has to purchase a particular radio spectrum and then allocate number of users to run their businesses. Therefore, multiple access techniques play an important role to allocate as many as users possible in that particular limited radio spectrum. And we have to do that in such so that the performance is optimal or high. And to do that, generally we have to do the duplexing and in either of time domain or frequency domain. These were the traditional approaches, right? So we'll go through some of the basic methods first because they are essential to understand the advanced methods. We will first cover frequency division duplexing. If we take the example of, let's say, the communication between a base station and a mobile station, there would be two different types of channels. First one is the downlink channel and the uplink channel. Downlink channel is also known as the forward channel, and uplink channel also it is known as the reverse channel. Now, duplex communication means simultaneously both the parties can talk to each other. That means simultaneously mobile station and base station, or the mobile user and the base station can talk to each other. How we do that? Generally, what we have done previously is we provide the frequency division duplexing by providing the separation of uplink and downlink or forward and reverse channels. Such as, let's say, in this figure we have seen this is a frequency scale. I can allocate certain range of frequencies for reverse channel, which is uplink channel, and certain range of frequencies can be allocated for the forward channel, which is downlink channel. Same thing is reflected here. So you can see that this particular channel is for the downlink and this particular channel is for the uplink channel. This was the basic idea of frequency division duplexing. Similarly, let's say time division duplexing. In that, we do not have many frequencies. There is only one frequency we have to establish the communication. However, we want to establish the communication between both mobile station and base station. How do we do that? We provide the time separations, such as, let's say, a particular time slot is given for the forward channel and the other time slot is given for the reverse channel. It will use the different time slots for forward and reverse link. And multiple users, they share a single radio channel, which means we have a same frequency for uplink and downlink, but the time slots are different, which is also known as the forward time slot and reverse time slot. This is the basic idea of time division duplexing. We are covering the basics first so that we can understand the advanced techniques very easily. The question comes, why do we need multiple access methods? The basic idea is we can have multiple mobile stations or multiple users, they can share a same radio channel without interference. And that's why we have to design the multiple access methods. We can have multiple access to the same channel also in different time slots that we have seen in TDD or time division duplexing. Multiple traffic channels can be used simultaneously also, such as, let's say, mobile station attached to a transmitter or receiver. Transmission from any mobile station is received by all other parties within the same radio range or same frequency range. Mobile station communicates with the base station via a traffic channel, a dedicated traffic channel not shared by other mobile users. So in that particular case, what we do is we provide a dedicated traffic channel also, or a dedicated frequency also, to a particular mobile station which is a high priority user. MS can hear the traffic. The problem with here is, let's say, if I have a mobile station, it can hear the traffic from many other channels also, such as, let's say, foreign base station or many other mobile stations also, or many other mobile users also. Therefore, mobile station must distinguish its own traffic from the other traffics which are potential noise for that particular mobile station. And how do we do that? Ignore the traffic from its own base station to other mobile station, because let's say if I am running here, this is my mobile station. My base station would be transmitting to many other mobile stations also, and I have to ignore that traffic too. Otherwise, that's a noise for me, and I may not be able to detect my own signal which is intended for me. Now, there is another case. Ignore the traffic from foreign base stations. If I am communicating with one particular base station, let's say here this, I may receive the traffic from other base stations also, which has to be filtered or ignored in order to receive my traffic correctly without any interference. Ignore the traffic from other mobile stations. We are surrounded by multiple users. Therefore, we have to ignore that traffic also. Otherwise, we will not be able to detect or receive our signal without any interference. Also, base station must distinguish traffic from different mobile stations too. Similarly, right, base station should be able to provide the separation between multiple traffics received from various mobile stations, right? So MS or base stations can distinguish this, and the special thanks goes to the particular multiple access techniques, which is based on the orthogonalization, right? Which is we will cover in subsequent slides when we cover that. Let's take a look at what is frequency division multiple access, which is also known as FDMA. Let's take a look at what is frequency division multiple access, which is also known as FDMA. A frequency division multiple access is known when we have different mobile stations are allocated with different frequencies, such as let's say here mobile station 1 is allotted frequency f1 dash. Mobile station 2 is allotted frequency f2 dash. Mobile station n is allotted the frequency of fn dash. And these are in the reverse direction or uplink direction, which means traffic is forwarded from mobile station to the base station on the dedicated channel, which are f1 dash for ms1, f2 dash for ms2, and so on. On the similar way, in the reverse direction, in the forward direction, which means in the downlink direction from base station to mobile station, separate frequencies are allotted, which are nothing but f1 to communicate between base station and mobile station 1, f2 to communicate between base station and mobile station 2, and so on. Which means all the communication links, they have dedicated frequency. That's why it is called frequency division multiple access. That's why it is called frequency division multiple access. If I look at the channel structure, here we can see this particular range of frequencies is allotted for reverse channels, which means from mobile station to base station, which is nothing but uplink, Whereas this particular range of frequencies, which are known as forward channels or allotted as forward channels, which are nothing but f1, f2, and so on, to establish the communication between base station and mobile station, which are nothing but in the downlink direction. And there will be definitely, to avoid the interference between two channels, we provide the specific guard bands to avoid the interferences between the two channels, right? So this is called the guard band. Now if I just combine and say this is a particular range of a frequency for first user and then the guard band, second user and then the guard band, third user and then the guard band. So the bandwidth, total bandwidth for one user would be this W, which is nothing but addition of the guard band and this particular frequency range. Now we can see that the total bandwidth is W equals to N, which is nothing but N number of channels times WC is nothing but the total bandwidth, guard band plus the frequencies which we have allotted. Same way, let's brush up TDMA, as these are essential to understand the advanced methods which we will cover soon. We have to go through the basics first. In TDMA, let's assume the frequency is same across all the users. We have limited frequency, let's say for a while one particular frequency for an example, and we have multiple users such as user 1, user 2, user 3. How we establish the communication so that they do not interfere with each other? The best idea is to separate them through the time slots. Which means one particular time slot is dedicatedly allocated to a particular user, right? And the carrier frequency remains same. However, they are split in terms of time slots across multiple users. Each frequency, now here the advantage is each frequency is efficiently utilized by multiple users, right? We are splitting them by the time slots. The problem is the wait duration would be higher because each user has to wait for it. For an example, this is a basic structure of TDMA, such as let's say these are the reverse time channels. Such as let's say mobile user 1 wants to talk to the base station and the frequency is same. However, it can talk only on the first time slot which is been dedicatedly allocated to mobile user 1. Similarly, mobile user 2 can talk to the base station in time slot 2, and so on for all n time slots it can go. Similarly, in the reverse direction, or similarly in the forward direction or in the downlink direction, which means base station wants to talk to a particular mobile station. In that case, it will also talk only in a specific time slot. Let's say base station wants to talk to a mobile user 1, then this is a particular time slot when it can send the message to the base station. That's how the system is time slotted. Everyone will get a fair time slot, and this is very useful when we have limited frequencies. The disadvantage is the wait duration goes higher. If we look at the basic structure of the TDMA transmitter would be like this. Let's say I got n number of messages, M1T, M2T, MNT. They go first into the buffer, will be stored in the buffer, and then we have a scan operation and we create the TDM stream, such as, let's say this is my frame. In slot 1, mobile user 1 can talk. In slot 2, mobile user 2 can talk, and slot and so on. So we frame their traffic in the slots, and this is my frame structure. Or you can call it a TDM stream, and put it on the channel for a transmission, transmitter. At the receiver side, TDM stream, which is modulated, definitely would be received, and at the end, again, there will be a scan operation across different time slots, and during those time slots, respective mobile station will decode the traffic. Now, moving forward, two duplexing modes for TDMAs are available. Moving forward, two duplexing modes are available for TDMA. Such as in TDMA also, we can have two different modes, one is called FDD, which is frequency division duplexing, and one is called TDD, which is time division duplexing. In frequency division duplexing, what we do is frequency for forward channels are different than the frequencies for reverse channels. That means in forward channels we have the slots. In reverse channels we will have the slots, means uplink we will have the slots. In downlink we will have the slots, but they are different in frequencies. So two different frequencies are used for uplink and downlink. Such as, let's say, F is used for all forward channels and F dash is used for all reverse channels. First figure, where you can see all forward channels, they are using a frequency F. All forward channels, they are using a frequency F, and for that particular channel, all stations are time slotted. So they can talk in between those time slots only. Whereas in the second figure, you can see all reverse channels, they are on the other frequency, right? F dash, not on F. Which means in the reverse direction, all the stations, they can talk to each other through that particular time slot only. The difference is uplink and downlink, they have different frequencies, which are again time slotted, which is called time division duplexing method of TDMA, which is also called TDMA/FDD. The next one is TDMA/TDD, which is called time division duplexing, means same frequencies for all forward and reverse channels. We use it same. F is for uplink, F is for downlink. There is no difference. Such as, let's say, TDMA/TDD, the figure shows frequency remains same for both the channels. But the communication is time slotted between mobile station and base station. This is called TDMA/TDD. TDMA/FDD is sometimes used to keep a separation between uplink and downlink so that interference can be avoided. Now, TDMA frame structure, if we take a look quickly, let's say these are the time slots 1, 2, so on. So in one frame, all n users will be allotted a single time slot with a specific guard band. So there will be a guard time, then there is a head, and there is a data. So this is called my frame for TDMA. Now this is used to minimize the interference due to the propagation delay. Sometimes there would be some sort of propagation delay and slots may overlap with each other and they destroy. Therefore, to avoid this, we provide a little bit of guard time. This is in a time domain, please note, it's not in a frequency domain. If it is in frequency domain, it was known as guard band, what we have seen previously. Moving on to the third traditional method. We are covering all the traditional methods first to brush up the concepts, and then we'll move to the advanced methods what we use in 5G and 6G, right? Code division multiple access, CDMA, code division multiple access. This is another method. This is another method for communication. Do not get confused between CDMA, which is with CSMA, right? CSMA is nothing but the carrier sense multiple access, where CDMA is nothing but code division multiple access. CDMA is nothing but code division multiple access, right? So here the idea is each user has the special code or a separate code. The separate code will be used per user, and using that the spreading happens. We'll see how the spreading happens quickly. So code sequences are generally orthogonal. Code sequences are generally orthogonal, and different users can use the same frequency simultaneously here. Now the advantage is various users, they can use the same frequency. However, they are separated in terms of a unique code, such as, let's say, this is my base station and these are my mobile stations, such as MS1, MS2, so on up to MSN. My mobile station 1 wants to talk to a base station. In that case, the frequency is, let's say, for uplink direction, all the frequencies are same. The frequency is F, which is same for all the mobile stations. However, a specific unique code C1 dash is allotted to mobile station 1, C2 dash is allotted to mobile station 2, and so on. Similarly, in the downlink direction, frequency again remains same, but when my base station wants to talk to a particular mobile station 1, C1 is the code. Base station wants to talk to specific mobile station 2, C2 is the code. C2 is the code. So that's how this is called code division multiple access with FDD, frequency division duplexing. Now see here, this is called frequency division duplexing. If I have misspoken this, please note that uplink and downlink, they have different frequencies. Uplink has frequency F and downlink has frequency F dash. Uplink and downlink, they have different frequencies. However, all the mobile stations on uplink, they have the same frequency F, and all the reverse forward downlink communication between mobile station and respective base station and respective mobile station, the communication between base station and respective mobile station is performed on F dash, right? Is performed on F dash. This is called frequency division duplexing for CDMA. This is called frequency division duplexing for CDMA across different codes, which is dedicatedly used for a different mobile station, right? There are two implementation methods. Traditionally, we have used that for CDMA, such as, let's say, direct sequence and frequency hopping. These two are the famous methods which we have used in the traditional systems. So same frequency for all forward and reverse channels, they are used. Now let's see the concept of spread spectrum for CDMA. So let's say this is my original signal ST. This is my original signal ST, right? This is my original signal ST, and we have the pseudo random sequence CT, which is used to phase modulate the data modulated carrier signal S of T to produce M of T. So now here I'm going to use my pseudo random sequence and multiply with my original digital signal, and I will get my spreaded signal here. You can see that my signal spreading is happening here, right? So, and M of T occupies the broader bandwidth and has the lower peak than S of T. Now, if I look at the direct, that was the basic concept of spreading. If I look at the direct sequence spread spectrum, in that what I do is I multiply the code with my digital signal and I get my transmitted signal here, which we have seen on the last slide. At the receiver side, again, a particular user, let's say MS1 here, has the code C1. The same code will be used here. Let's say C1, MS1 has multiplied and spreaded its signal. The spreading happens. After that, it has transmitted. At the receiver side, let's say the same code has to be used, or respective code which is exactly the same has to be used here for despreading the signal, and CD is synchronized, and then the signal is recreated. The signal is recreated, right? The signal is recreated. Pseudo-random sequence CT phase modulates the data modulated carrier of S of t, producing M of t, and M of t generally they'll occupy the broader bandwidth here, and then again I multiply the same code and reconstruct at the receiver side. On the contrary, the other concept is frequency hopping. Instead of using this one code, here I am using a frequency hopping pattern, which will spread the signal in the form of a frequency comp. Here you can see it is spread in that particular multiple segments. Here you can see, that's why it is called frequency hopping. And at the receiver side, for despreading, I will use the same hopping pattern. And I will try to reconstruct my signal. This is also known as FHSS, frequency hopping spread spectrum for CDMA. This we have used across many time in the previous generations, or in the maybe LTE and somewhere else, right? Pseudo-random hopping pattern, this is used as to change the signal pattern as we have seen here, and then it is transmitted, and at the receiver side again the same pattern will be used. Now there are a few problems. Very famous problem is called near-far problem. So let's say assumption 1. The transmission power of, let's say, mobile station 1 here is equals to the transmission power of mobile station 2. Let's say both the mobile stations are transmitting the same power. However, the distance of both the mobile stations from the base station are different. Such as, let's say, mobile station 1 is located at D1 distance from the base station, and mobile station 2 is located at D2 distance from the base station. Now, because of this distance, received signal strength, which is known as RSS, for mobile station 1 at base station is higher than the received signal strength of mobile station 2 at base station. Received signal strength of mobile station 1 is larger than mobile station 2, naturally, because it is located closely to the base station. Now, second assumption is, let's say mobile station 1 and mobile station 2 use adjacent channels. Mobile station 1 and mobile station 2 use the adjacent channel. That means the out of band radiation of mobile station 1 will interfere the signal of mobile station 2. The out of band radiation of mobile station 1 which will interfere the signal of mobile station 2. Now please note, this is a separation of distance, but let's say at here they are using the adjacent channel, then the frequencies, they are located adjacently and they'll interfere because of the signal strength and the frequencies allotted like this, such as, look at this one, this is my MS1 which is located here, and this is my MS2. They are using the adjacent frequency channels such as F1 and F2. They are located besides each other. MS1 is closely located with the base station, so the received signal strength is larger, whereas MS2 is located far away from the base station. That means the received signal strength is lower. That's why this adjacent channel interference can be a serious issue, and we must keep the out of band radiation as least as possible to avoid this kind of interference, right? And this you can see here also, adjacent channel interference and spread spectrum system in CDMA, where you can see when we have a baseband signal, the adjacent channel interference can be specifically serious in the spread spectrum technique used, because when we despread, those adjacent channel interferences, they come and they will destroy or collide with my intended signal which I am trying to receive. So that's why this is very serious. Now the simple solution is the power control. Let's say there are two alternatives. control the transmit power PT at mobile station 2, right? And receive power PR of the adjacent channel interference from mobile station 2 is controlled. Now CCIR, you can call it a co-channel interference ratio, is controlled by controlling the power. So let's say whichever the power we don't want to receive too much, we can control that at the transmitter side. That is one simple thing. Or control the power station of mobile station 1, which is also possible, right? In this particular case, let's say here mobile station 1 is creating the interference heavily. Mobile station 1 is creating the interference heavily on mobile station 2. What I can do is I can control this power. What I can do is I can control the power PT for mobile station 1, so that the received power PR of mobile station 1 is controlled, kept not enough strong, so that we can receive this signal very easily. So I'll pull it down, or I can adjust this, right? So by these power adjustments, we can overcome this near far problem. That is one simple solution. And what the formula is used is PR by PD is equals to 1 by 4 pi dF divided by C raised to alpha. PT is nothing but the transmitted power. PR is nothing but the received power in free space. D is nothing but the distance between the transmitter and receiver. D is nothing but the distance between the transmitter and receiver. F is nothing but the frequency of transmission on which it is transmitting. C is nothing but the speed of light. And A is nothing but the attenuation constant. A is attenuation constant. Now, so far what we have covered were very basic methods. Now we will start moving to a little bit of advanced techniques. Such as, let's say, in this particular section, we will cover space division multiple access. In this particular section, we will cover space division multiple access. Now in SDMA, omnidirectional space is divided into the spatial sectors using the smart antennas at the base station. So such as, let's say, I got omnidirectional space. What I do is I use that particular space in a particular direction to allocate a particular beam for a space separation. So let's say beam 1 is allotted on MS1, beam 2 is allotted on MS2, and so on. Right? So the smart antennas focus gain in desired direction, allowing multiple mobile stations to share the same channel, right? Smart antennas focus gain in a particular desired direction, allowing multiple mobile stations to share the same channels. Now this is equivalent to beam forming. So here you can see I can control the gain for the user which is far away located, and I penetrate my beam, or I can focus my beam at a higher intensity in a specific direction. Focused beam extends the range and reduce the number of required cells. Now I can see that what I can do, instead of having multiple of cells or base stations deployed, I can do the specific beam forming in a specific direction in such a way so that the power is high in that specific direction, kind of a pencil beam, and provide the coverage to that particular user. They also minimize the interference by limiting the radiation towards the undesired direction. So such as, let's say, I am not interested to transmit in any other direction. So what I have to do is I have to cut down that transmission and do not radiate across everywhere, or kind of an omnidirectional antennas, right? I don't do that. What we do is we provide a specific direction, and then in that only we do the beam forming. Such as, let's say, this is a particular scenario. Such as, let's say, this is a particular beam which is focused on that particular mobile user to provide the coverage. That's how we use that space division multiple access with reference to the advanced mobile communication technology, which uses beam forming, right? Let's see the new radio multiple access technologies or methods for 5G and beyond, or 6G and beyond. OFDM is also known as orthogonal frequency division multiplexing. Here what we could do is divide a high bit rate stream into the several low bit rate streams, right, by using the serial to parallel conversion. Now in the traditional communication, what we do is we transmit the entire signal. We do not divide them into smaller parts, or we do not take the individual symbol and put it across different frequencies. What we do, we take that entire signal and put them here and put them here. Now, this is inefficient. To overcome this, people came and said, let's use OFDM, orthogonal frequency division multiplexing, and based on that, multiple users will access, which is called OFDMA, which is called orthogonal frequency division multiple access, which divides a high bit rate stream into the several low bit rate streams, which is robust against the frequency selective fading due to the multipath propagation, which is robust against the frequency selective fading due to the multipath propagation. The basic idea is can be visualized on this slide. So here you can see that the left hand side figure represents the single carrier transmission. Left hand side figure represents the single carrier transmission, and right hand side figure represents the multi-carrier transmissions, which is nothing but the OFDM. So here you can see, let's say, my different symbols, or you can say different bits, if you assume just BPSK, 1 bit per symbol. So different symbol is transmitted, right, is transmitted here, but not on different frequencies, on the same frequency. So the frequency is same for all the bits or all the symbols. This is called a single carrier transmission. Definitely you can have the time slots for each symbol. However, in OFDM, we generated the orthogonal carriers which are separate in frequencies, F1, F2, F3, F4, F5, so on. And we picked up several bit symbols, right? So let's say if you are using BPSK 1 bit per symbol, if you are using QPSK 2 bits per symbol, if you are using advanced version, let's say 16 QAM 4 bits per symbol, they'll be put on that particular frequency. So let's say this is frequency 1, which will transmit this particular symbol. Frequency 2, which will transmit this particular symbol. So you can see and visualize this kind of a fountain, right? This is kind of this fountain. Now here you can see all of those are transmitted at the same time. All of those are transmitted at the same time. This was the basic idea of OFDM. There is an advanced mathematical model behind this, which we have to go through when we go to the particular scheme and study in more detail. However, I have covered few basic equations here for your reference. So generating, how we generate OFDM signal, how we generate OFDM signal, right? The question is how we generate OFDM signal. Now let's say symbol can be QPSK, BPSK, QAM, any, right? Let's take a particular symbol and put it on a particular subcarrier I at the time K. Take a particular symbol, let's say take this particular symbol, put it on a particular frequency carrier Fi or ith frequency on a particular time K, right? And the other symbol alpha bits, they can also be used, such as let's say BPSK or QAM or any version of QAM, MQAM. Use it, that's okay. Any symbol, we pick it up and put it on a carrier, so frequency carrier I, which is generated through OFDM signal. And see here how we do that. So the baseband signal is generated by DSP. So now let's say this is my SBPIKT. So this my, now when I multiply with WT minus KD times, this is XIK exponential, this is my carrier which is I am interested in. Now see, this is my carrier which is I am interested in, right? So this is particular, you can see these are XIK is nothing but a symbol. So here you can see this is my symbol. This particular symbol goes on that particular carrier. The next symbol goes on a next carrier. The next symbol goes on a next carrier. The next symbol goes on a next carrier. So that's how I am splitting and putting them on OFDMA. Right? And this is my subcarrier. And this is my subcarrier. This is my subcarrier. And this is my window function. This is my window function. How it looks? The spectrum of modulated data symbols, they are visible here. The spectrum of modulated data symbol, they are visible here. You can see there are various frequencies which are orthogonal with each other, and they are carrying different symbols, what we have just discussed. Rectangle window function of duration t0 was used, and it has a sync spectrum. And now here you can see that the subcarriers which are generated here, they are orthogonal with each other. So the problem here is there are n particular subcarriers and they overlap with each other here. You can see that this tail end. Now we'll look at how to resolve that problem also. But this is the composite signal which carries n subcarrier, and you can see as PBKT is equals to WT minus KT, which is nothing but the window function times summation of I equals to 0 to n minus 1, which is nothing but the index to represent a particular carrier frequency, and xik is nothing but the symbol what we have just seen, and e power j 2 pi I delta ft minus kd is nothing but a carrier. It's nothing but a carrier, right? And now how do I see this? So if I look at this OFDM transmitter and receiver, let's say I got my data here, all the symbols, correct? So that constellation diagram I've just shown. Now those symbols are taken here, let's say out of this x0, x1, x2, so on. I take the inverse fast Fourier transform. Then I take the real and imaginary components, and then I perform the DAC, like digital to analog conversion. After that, I multiply with the carrier frequency FC, one version here, and the 90 degrees phase shifted version on the other wing, and I take the summation and I generate S of t. So this is my transmitter. At the receiver side, I will receive. Firstly, I have to multiply the same frequency here in the coherence FC, and then two frequencies are orthogonal to each other, which are 90 degree phase shifted, and then I'll receive it, and then I'll do the fast Fourier transform, and then I will extract my symbols through the detection method, and then give the symbols, and then give that signal to a particular user. Now there are multiple problems. There are several problems with OFDM, right? To overcome this, we have to design the advanced version of my scheme, such as, let's say, spectrum overflow. Here you can see this is one spectrum of a carrier. I am doing the multiplexing, which means I will have multiple of those together in the multiplexed manner. Definitely they are frequency splitted, but the separation is sufficient, but this side lobes, they will overlap with each other and they will destroy the signal. The entire band should be same. Entire band should use the same subcarrier spacing. Now this is a second problem. Now let's say this is my carrier 1, carrier 2, carrier 3, so on. They have to use the same subspacing. This is one more problem. Entire time should use the same symbol size and cyclic prefix. Now this is the second problem. Third problem. All users should strictly time synchronize in the uplink. Now this synchronization sometimes is also difficult, right? These are the four problems, how we handle and how to overcome these limitations, and go for the next one. Now basic difference. What is the basic difference between what is the basic difference between FDM and OFDM, right? Basic difference between FDM and OFDM. See, FDM, that means frequency division multiplexing. We were multiplexing multiple frequencies, let's say channel 1 for user 1, channel 2 for user 2, and in between we used to have the guard band. Now this is to avoid the interference. But we did not use the orthogonal frequencies. That means we need the guard band to overcome the frequency, to overcome the interference. However, you can see because of this, there is a destruction or wastage of the bandwidth. We are not using our bandwidth optimally. The basic idea in any communication system is to multiplex as many as users simultaneously and provide the service or communication to the larger number of users. To overcome this, people have invented or researched OFDM, where you can see we were using the orthogonal frequencies and squeeze the channels in the bandwidth so that they are forced to use the lesser bandwidth. Moreover, the frequencies were orthogonal, 90-degree aparted. See, the frequencies were orthogonal. So the carriers were orthogonal to each other. The frequencies were orthogonal to each other. So we could transmit same number of channels in half the bandwidth. So the saving is 50% of the bandwidth, which means we can additionally subscribe double number of bandwidth. So we can give other 10 users or other 10 channels in this particular bandwidth range. This is the basic difference between FDMA and OFDMA. There is one more method which called filtered bank multicarrier, FBMC, filtered bank multicarrier. Now, as we have seen the first problem, that there were side lobes. Here you can see these are my bands, right, which were overlapping with other carriers. To overcome that, the simple solution was innovative, and they used a filter to remove the subcarrier overflow. They used a filter to remove the subcarrier overflow. That means no side lobes. That means no side lobes. We have eliminated the side lobes. If we eliminate the side lobes, if you go and study the OFDM very nicely, we don't have to use the cyclic prefix also, right? Which will cut down the complexity, and we can transmit more bits per hertz also, right? And different users can have different subbands with different parameters. Different users can have different subbands with different parameters. So such as, let's say here this is my actual signal, right? Let's say a single OFDM carrier. Here this one. So you can see this is my single OFDM carrier. What I'll do is I'll pass it through a particular filter and cut down this to side lobes and cut down this to side lobes, or you can say that overflow. So now what I get is this clean signal, and I can just multiplex this in this way. So this is, you can see right hand side figure where I'm pointing, you can see these are my clean signal. Now here you can see this is my user 1, which is allotted 5 different carriers. This is user 2, which is allotted, let's say 7 different carriers, and this is user 3, which is allotted, let's say multiple different carriers. Now you can have one carrier for one user also. That is also possible. That is also possible. One carrier for one user, that is also possible. There is one more case. So this I have just shown you. Now one carrier for one user that can be allotted, but this is an advanced version. Let's say some of the users, they'll ask an entire band, that I want a particular band, right? So what you can do is you can have, let's say, an entire band, OFDMA 1, OFDMA 2, OFDMA 3, right? So subband 1, let's say with the spacing of 10 megahertz, right? Spacings can be different. These frequencies are indicative. Subband 2 could be, let's say, different spacing. Subband 3 could be, let's say, different spacing, right? So bands, a particular band is divided into multiple subbands. So let's say this is my larger band, and it is divided into the smaller subbands. For each subband, it may use the different OFDM parameters to optimize this particular application also. So let's say in this, I'll frame my OFDM differently, that particular subband. In this, I'll frame my OFDM carriers differently with that particular subband. Similarly for other bands too, right? And each subband spectrum is filtered to avoid inter-subband interference also. Which means it is a spectrum filtered version, right? It is a spectrum filtered version, which is also known as spectrum filtered version, FOFDM, because each subband spectrum is filtered to avoid the inter-subband interference, right? Different users or subbands, they do not need to be time synchronized here across the subbands, right? So it's kind of an asynchronous OFDMA. There are two advanced versions. There is one more advanced version which is called GFDM. There is one more advanced version of this which is called FDM, is called GFDM, which is nothing but generalized frequency division multiplexing, Here you can see in this OFDM, what we have done is we have allotted different carrier frequencies to different symbols or different data streams, right? Whereas here in GFDM, what we have done, instead of giving that entire band and distributing across different things, what we have done is we have specifically segregated them in terms of blocks, and then we have done the allocation, right? That's the advantage. Only difference is we have done the block-wise FDM, So far what we have seen were the very popular methods of frequency division multiple access. Now let's say the next version is NOMA. Next version is of the multiple access is NOMA, which is called non-orthogonal multiple access, The basic concept of non-orthogonal multiple access is to leverage the disadvantages of the previous methods. So the basic concept behind non-orthogonal multiple access NOMA is to serve more than one user in the same resource block. In the same resource block, we want to serve more number of users. The resource block could be the same time slot, could be the same frequency, could be the same spreading code, or could be the space. So NOMA can be hybridized across multiple methods. So it could be on time slots, it could be on frequencies, could be on different spaces, it could be on different codes, right? Codes for CDMA, frequencies for FDMA, time slots for TDMA, and spaces for SDMA, right? So NOMA can be the advanced version of all of them. And the advantages compared to the orthogonal multiple access, it provides a massive connectivity. It lowers the latency also, because everyone gets the access at the same time, or at the same frequency, or at the same code, or at the same space, right? Only the powers are different. I'll explain how it goes through. And then it increases the reliability and improves the user fairness and spectral efficiency. Now let's see the basic concept. So let's say, look at the diagram. Let's say this is my base station, and these are two mobile users. So now this is mobile user 1, and let's say this is located nearby my base station. Now here you can see this base station is nearby my this mobile station is located nearby my base station, so I don't need to transmit very heavy power for that. Even though if I transmit a little bit of power, it should be able to understand and receive the signal, because it is located nearby with the base station, nearby to the base station. So smaller power is transmitted. On the contrary, this mobile user is located far away from the base station. That's why I have to transmit larger power for this. So that's why you can see this pink allocation of the power is larger for the second user. However, please note the frequency is, now I am allotting the same frequency range for both the users. Frequencies are same. Same frequency range has been allotted for both the users. Same way, if it is with reference to the space division multiple access, you can use NOMA with the concept of SDMA, saying that same space will be allotted. If it is time division to multiple access, we can use the NOMA and use a different power transmission, saying that the same time slot. If it is a frequency division multiple access, that we have discussed. If it is time code division multiple access, let's say use the same code but use the different powers for transmission, right? So that's how the NOMA works. Now you can at the receiver side we'll take a look. So at the receiver side also I'll explain you here that successive interference cancellation method is used. So let's say here you can see the user which is located nearby, right? The green signal, what it does, it will do the successive interference cancellation for this larger power, and it says, okay, this is my power and I will receive my signal. Whereas the user which is located with the larger power, definitely the power strength will be received to him is at a larger scale, and it will consider other lower powers, which is for this user lower power, which will be considered as a noise and ignored, so that it can just detect this ping signal very easily. We'll look at that in more detail a little bit of later, right? So now look at this NOMA, which is known as non-orthogonal multiple access. You can see NOMA. So let's take a look at this difference. So let's say OFDMA first. MA, do not get confused. Again, it's MA means multiple access. When multiple users, they try to access the channel or infrastructure or resource, then it is called multiple access. And the basic scheme is called OFDM, or orthogonal frequency division multiplexing. And MA comes when we try to access multiple access. So concept is same. Now let's say there are two users, user equipment 1 and user equipment 2. So you can say this is UE1 and UE2, right? If it is OFDMA, what I'm going to do is I'm going to have, let's say, the different blocks of frequencies are allotted to both the users, right? Different frequencies are allotted. But what I'm going to do is I'm going to put the same power transmitted. Whereas NOMA, what it does is we say, okay, allocate the same frequency range for both the users. So you look at this, the range of frequencies is same for user 1 and user 2. What is the difference? The difference is I separate them in terms of power strengths, right? For user 1, which is located nearby the base station, so I transmit lesser power. For user 2, which is located far away from the base station, so I transmit larger power. And according to that, I can detect the signal by using successive interference cancellation, which is known as SIC. If we do the comparison between orthogonal multiple access and non-orthogonal multiple access, you look at the diagram in orthogonal multiple access, which is at the left side, a specific frequency resource is assigned to each user, even it experiences a good or bad channel condition, doesn't matter. Thus, the overall system suffers from low spectral efficiency and throughput. Now, what we do is we allotted a specific frequency resource to the user, right? So now that could be a little bit of blockage also, that other users may not be able to access that frequency because it is allotted. Whereas in NOMA, on the contrary, in NOMA, the same frequency resource is allotted to the all mobile users. So you can see all mobile users, they can access whichever this frequency, entire frequency range, but the powers transmitted for different users, they are different. Right? That is the difference. However, at the receiver side, they must use successive interference cancellation to eliminate the power of the other users which are not of interest. Therefore, the probability of having improved spectrum efficiency and high throughput is considerably increased, because see, we have the simultaneous access of entire frequency range. We can just separate them in the power domain, and now this can be over the codes, over the frequencies, over the time slots, over the space. So very good, right? So NOMA can be used along with the beamforming also, right? So that's really good. Now user fairness is higher. Latency is lower, definitely. See, user fairness is higher. Why? Because everyone gets an access to that entire band. Latency is lower, definitely, because all the users, they are able to access the channels quickly, so that they can quickly transmit, so that overall latency goes down. Massive connectivity, definitely, because all the frequencies are available for all, the entire range is available for all the users. So the connectivity is massive. In OMA, for an example, let's say OFDMA, when we do the scheduling, correct? User with a good channel condition, they'll get the highest priority to serve, right? To be served. And user who has the bad channel condition, they'll wait for the access. They'll not get the quick access, which will lead to a fairness problem, right? And it will add up to the latency. Latency goes high. Now, this approach cannot support a massive connectivity, which we are expecting in 6G or 5G and beyond, right? However, NOMA can serve multiple users with different channel conditions simultaneously. I've explained that. Therefore, it can provide improved fairness, lower latency, and higher massive connectivity, right? These are the advantages. Let's see the downlink NOMA network. Let's see the downlink NOMA network. So for an example, these are my, let's say, these are my messages which I want to transmit from base station to the multiple users such as user 1, user 2, user 3, so on up to user L. And these are the respective right signals. And all of those are, let's say, the signal which is nearby my base, the user which is located nearby my base station, I will transmit lower power. And the signal which is far away from my base station, I will transmit highest power, right? So here U1 is located far away and it gets largest power, and UL is located nearest to the base station, so that gets lower power, and then I transmit. At the receiver side, U1 naturally has the largest power, so what it does, it detects the signal for its own, and other mobile stations power or other users' power, they are lesser. So that's a noise for it, and it will ignore it. User 2 has the second largest power. So what it has to do, it has to do the successive interference cancellation for U1 and ignore the lower powers for other users which are having the lesser power received compared to U2, right? So for this, we don't need to do the successive interference cancellation. We can just ignore it. But we have to do the successive interference cancellation for U1 and receive the signal for U2. Similarly, for UL, do SIC for U1, U2 and UL-1 and receive the UL signal which has been transmitted from the base station. Now so on, we keep doing it, and for UL, we do the SIC for U1, U2 up to U capital L-1 and receive UL, which is my signal for user UL, right? So this is my downlink NOMA network. This is an explanation of the discussion what we have just rationally produced here. Let's take a look at the uplink NOMA network. Now let's say uplink, that means users are transmitting towards the base station. So X1 comes here, it gets transmitted for U1, X1 comes here, gets transmitted for U1, then X2, and so all these messages, they come, and base station performs SIC for all the stations or all the users, and then it will receive the signal from both the from all the base stations. So in uplink NOMA network, each mobile user transmits its signal to the base station. At the base station, SIC iterations are carried out in order to detect the signal from the mobile users. So base station will perform my successive interference cancellation and then detect the signal by assuming that the downlink and uplink channels are reciprocal and the base station transmits power allocation coefficients to the mobile users. Now it says base station has provided the power allocation coefficients based on their distances, right? Such as, let's say, the one which is closely located. See, remember in this transmission we have seen the one which is closely located gets lesser power. So same way that user will come to know that I have to transmit lesser power in the reverse direction, in the uplink direction also, because downlink direction lesser power came because I'm located closely to the base station. Same way other users will come to know about their power coefficients which they have to transmit, from here to there, right? So those base station transmits the power allocation coefficients to the mobile users, and the received signal at the base station for synchronous uplink NOMA can be expressed as this particular formula, right? So R is equals to sigma I equals to 1 to L, which are nothing but all users, HI square root of AI P xi plus N, where here you can see HI is nothing but the channel coefficient of the channel for that particular user, that channel coefficient. P is the maximum transmitted power maximum transmission power assumed to be common for all the users, so that that's the maximum power which we can transmit. And AI is nothing but the power coefficient which will scale this maximum power. So let's say UL is located closely, right? So let's say 0.2 into P, because it should not transmit too much of power. And let's say here this is next user located a little bit far, 0.3 into P, then the 0.4 into P, and so on. Let's say P, that is full transmission at a max power, because this is located very far away from the base station, and N is my noise. Okay, N is my noise. The advanced version of NOMA. The advanced version of NOMA. See, there is an advanced version of NOMA, the next technique, which is also called cooperative NOMA based on SDR, right? Software defined radio, cooperative NOMA. So here you can see that cooperative communication, the famous idea of using a relay in between to reproduce the signal to improve the signal strength. Relay is used to reproduce the signal to improve the signal strength, right? Where the transmission between the source and destination is in cooperative communication, where the transmission between the source and destination is maintained by the help of one or multiple relays, which means, let's say I have a relay here, and it can receive the signal from the base station, improve the signal quality, and transmit it further for the users. If I do not have a relay in between, the direct communication doesn't work, because the quality of service or the signal quality goes very low. So that's why these relays, they extend the coverage area and increase the system capacity, right? And at the same time, by reducing the deterioration of the performance, means we can have the better performance. The performance reduction or deterioration because of the multipath fading is reduced when we use the cooperative communication. Now, we use NOMA on top of this basic concept. Therefore, the combination of cooperative communication and NOMA, some of the researchers have proposed, and they considered it as a remarkable solution to extend the NOMA technique on cooperative communication, right? Where what we do is, users, they have, those who have the stronger channel conditions, they are considered as relays. So let's say this has the stronger channel condition, because it is located closely to the base station. So it will receive the signal nicely with lesser deterioration of the signal quality. Whereas these are the users which are far away located, right? Which means they do not have the stronger channel condition, right? So the users with the stronger channel conditions are considered as relays due to their ability in decoding the information of the users to assist the users, those who are having the poor channel conditions. So it will help to decode the signal, because it will just reproduce the signal and improve the quality here. The next version, in this particular section, we will take a look at a particular scheme called RSMA, which is nothing but the rate splitting multiple access. The overview of this RSMA is nothing but it's a next generation multiple access technique that enables flexible and robust interference management. It generalizes and bridges SDMA and NOMA method. It generalizes and bridges or hybridizes both of them, SDMA and NOMA method. What it does, the key principle or the first principle is, each user's message is split into the two parts. So let's say this is my user message, and I will split them into two parts. One is, let's say there are two messages, W1 and W2. One is the common part and one is the private part, right? One is the private part. So one is the common part. These are the common parts and these are the private parts. So W12 and W12. W12 is the first message is common part. W212 is the second message is common part. Now these two common parts are merged and combined together and transmitted further through the, proceed further to the encoder, and then so on, transmitted over MIMO and NOMA MIMO, and then at the receiver side we do the successive interference cancellation, and then we'll see that subsequently. And the private parts of the messages, such as let's say W11 and W12, which are nothing but the private components of W1 and W2 messages, they are transmitted separately, right? So the private parts decoded only by the intended users only, they are not combined. So but the common part, they are decoded by the all users and they will be combined. Now this saves a lot of energy, this saves a lot of bandwidth, this saves a lot of resources, because let's say many of the users or frames, they have common part. We keep transmitting repeatedly. Instead of transmitting them repeatedly, what we do is we can transmit them in a combination, in combining them. The common part can be combined and transmitted selectively or once or twice, right? Limited times, whenever it is needed. Whereas the private parts or private elements of the message, of the different messages or users, they can be transmitted differently, right? So that saves huge bandwidth. At the receiver side, each user first decodes the common message using successive interference cancellation. See, at the receiver side, they will receive all the messages, right, which are common. So they have to do the successive interference cancellation. What they can do is we can use NOMA and allocate different powers here. Let's say W112 has power P1, W212 has power P2. Pass it through the successive interference cancellation and execute NOMA's receiver, and then we can do that. So that's the hybrid version, right? That's the hybrid version. That's called rate splitting multiple access. That's called rate splitting multiple access. Then they decode their private messages and treat others as noise, right? Treat others as noise. There are several advantages of RSMA compared to other methods. There are several advantages, and which is the most state-of-the-art method which researchers have proposed for the advanced communication systems such as 6G or 5G and beyond. There are advantages such as, let's say, efficient interference management. The interference is efficiently managed here. Balanced user fairness and spectral efficiency. Spectral efficiency is increased definitely because we are not transmitting common parts or common elements repeatedly. User fairness, definitely because we are saving the bandwidth, which means the leftover bandwidth which we have saved can be given to the other users. It is very robust to the imperfect channel state information also, right? And the complexity, so it is lower complexity compared to the linear precoding. And the most important advantage is it is scalable with reference to multi-antenna systems such as MIMO and multi-user scenarios, right? It is scalable such as MIMO and multi-user scenarios, particular cases, right? So now, in this particular slide, when we are wrapping up and looking at all the multiple access methods all in all together, there are three major components. One is advanced multiple access technologies, which we are talking about right now. We have covered the basics, but those are just to brush up the concept so that we can understand these advanced multiple access techniques very easily. One is OMA, which is nothing but the orthogonal multiple access. One is NOMA, is nothing but non-orthogonal multiple access, and third is rate splitting multiple access. In orthogonal multiple access, what we have seen is modulation based on pulse shaping. So here we have seen filtered bank. Some of them we have seen, some of them in the interest of time I have listed here, so you can go through the research papers and learn at your own later after the seminar. So filter bank multiple carriers, or FDMC, this is one method we have seen. Generalized FDM, right? GFDM, that also we have seen. In OMA, there is another category called modulation based on subband filtering, where UFMC, universal filtered multi-carrier system, can also be possible, or filtered OFDM, FOFDM, that we have seen, that is also possible, right? The other one, UFMC, you can explore at your own through the research papers if you are interested further. OMA, there is another one, let's say single carrier DFT spread OFDM, or orthogonal time frequency and space, OTFS, orthogonal time frequency and space, right? So there are some of the methods you can explore. Now, and in NOMA, we have seen power domain NOMA, right? We say that NOMA can be on anything, right? It can be on frequency domain, it can be on power domain, it can be on time domain, it can be on space domain also. Only thing is we are changing the power levels for different users and keeping the other resource same or in the blocks, right? It could be the code domain NOMA also. There are different versions of them, such as, let's say, sparse code multiple access SCMA, low density spreading LDS, multi-user shared access MUSA, right? And the next one is NOMA multiplexing in multiple domains, like such as, let's say, pattern division multiple access, or lattice partition multiple access LPMA, or bit division multiple access BDM. There are several versions available. You can explore based on your research interests. Third technique what we have just seen was rate splitting multiple access. We have seen that in more detail. Further, you can refer to that particular research paper, right? So this was the research paper. From that we can refer and read more about RSMA, right? That's all I have for today's session. Thank you very much for your time and attending the session.